So we'll present our talk today on cyber risk assessment using large language model based agents and graph data science. I'll let my colleagues introduce themselves when they talk in the interest of time. So let's get started. Next slide. Uh, So we have a packed agenda for the next 30 minutes. We'll start with talking about how we are seeing the maturity of AI in security applications. Then we'll talk about a cognitive architecture for a security co-pilot that we have come up with. So this is addressing very specific security concerns that we'll share more details on. And then we'll show this in action. We'll look at how a modern security ops center can take advantage of artificial intelligence and particularly generative AI. And my colleague Venki, who has actually worked in a SecOps center, will actually talk about how GenAI is enabling this. Also, specifically focusing on graph databases, we'll talk about how graph databases provide an advantage and help to ground the generative AI models. And then we'll show a quick demonstration of how we have built some of the security, like a couple of use cases of the security copilot. And then Sadashiv will talk about our under the hood, what is happening with our security copilot, the graph data science algorithms. And feel free to keep your questions coming on chat. We'll try to address them at the end or offline. So let's get started. We have a lot of things on the agenda. Next slide, Vicky. So to start off, we are seeing AI kind of take over almost everywhere, especially with the ChatGPT explosion. And if you look at the applications that are built, we go back to this wisdom pyramid, so to say, by Jay Rowley, where you have the initial maturity where applications use a lot of data in unstructured form and they try to make sense of data. We move up to information, then to knowledge. Knowledge is where we have connections between different data sources, real world connection. And this is where graph databases can really help us to capture knowledge and make sense of the knowledge. And then finally, we want to get to a level where there are automated, actionable insights. And with the large language models, there is this concept called agentic workflows, which help us automate a lot of, more than automate, make these systems intelligent and try to get us to this wisdom level. So this is how we are seeing evolution. And as we move up the pyramid, you can see that the amount of the volume of data reduces. So initially, you have a lot of this, tying this to a security domain, you have a lot of logs, unstructured PDF report feeds, etc. But as we move up, we try to structure them into reports, dashboards. With knowledge graph, we try to give a single source of truth by connecting different data sources and having one view of a single pane of glass for understanding our enterprise, which needs to be updated in real time. And then we try to get real-time insights from this different applications. And as we move up the pyramid, the value obviously increases. We have high-value applications built using generative AI, but at the same time, there is a high risk. We are now letting the AI make a lot of decisions, so the risk is obviously high. So we want to be at a stage where we can control the risk, and a knowledge graph layer can actually help us build the systems in a responsible manner, and we'll show some examples of that. One other thing we see as we move up the pyramid is the human cognitive load becomes less and less. Like initially, when you work with data, the human has to do a lot of processing. You show them reports, they have to do less processing. You give them a connected nature of which asset is at risk and which other assets are at risk. They have to do still less processing by themselves. And if you get to a wisdom level where you have an agentic workflow to do this operation, then the human just has to supervise and make sure that the system is not getting off the rails. And that is the level we want to get to. So this is in a nutshell the level of security, and type this to the cognitive load. These new systems, we are coming up with something called a cognitive architecture, where we are moving away from traditional ML, but getting into this large language models, large multimodal models, and building generative AI powered applications. So next slide. So here, looking at security, so we looked at the security domain, and there are four major areas that we saw where AI and generative AI can really help. One is threat intelligence, where you capture threat feeds from multiple sources. And traditionally, the security industry has struggled to kind of give a good structure to these feeds. And now with generative AI, we can process these feeds in unstructured format like PDFs. We can even process websites. So if a website is publishing reports, we can directly take those and find indicators of compromise. So threat intelligence is definitely getting affected by generative AI. The network state being maintained, we are moving away from traditional databases to graph databases, which can capture a lot more complex relations. A response. So we are building security orchestration systems where we can control the response and give bespoke reports. And finally, automation, where we get into the agentic workflows, which we'll talk about. So, real quick, four emerging patterns that are coming out as we look at applying Gen AI and AI to security. One is processing of unstructured data. The threat intelligence doesn't, we don't need to spend effort and money to structure the threat intelligence. We can consume it as is and use generative AI to reason from it. We use knowledge graphs to provide a single source of truth. So the entire enterprise using network scans, etc. We consume this knowledge, keep the knowledge graph updated, and give a real-time perspective. We customize our responses based on a particular user. So relevant to that user, we can even give very customized bespoke reports. And finally, we use agentic workflows where you use the large language model to do the planning. So we take the human level of intelligence and cognitive effort, put it in a system where the LLM makes the plan. Or, for example, and this is very valuable in security, if there is a new attack that has come into play, you need a human to figure out what exactly has to be done. Those sort of steps can be composed and put in an LLM, and an LLM can actually give you a reasoning why a particular path has to be taken to counter that attack. So this can help us counter attacks which we have not seen in the past. So there is huge value in applying generative AI and this cognitive architecture to security. And now we'll show you some examples. And let me actually pass this to Venki, who is actually our security expert who has worked in this domain, and let him share insights of how we are doing this with some examples. So Venki, if you want to quickly introduce and start.
Hey, thank you, Dattaraj. I hope I am audible.
Yes.
Yeah, so my name is Venkateshwar Tyagi. I have around 7 years of work. I used to work in cybersecurity before joining Persistent. And in Persistent, we are trying to utilize how we can leverage AI and Gen AI, even knowledge graphs, in order to improve the cybersecurity operations in general. Also looking at security of Gen AI. So moving on, as Dattaraj mentioned, that once we wanted to create a use case in security operations, we wanted to understand the whole value chain from start to finish. And for that, we actually leveraged our internal cybersecurity team. We have Persistent has a cybersecurity consultancy, and we provide sophisticated solutions to our clients. We sat with them and we understood the whole value chain end to end. So just to walk you through that value chain, to start with, data comes from multiple sources. It could be network devices such as firewall, applications, cloud, resources, endpoints, servers, etc. And they are accumulated in one particular place. So let's call that place SIM, which is Security Incident and Event Management Tool. In parallel, threat intelligence comes, and at SIM level, correlations are done. Due to those correlations, alerts are generated, and those alerts are sent to security analyst level 1. So the job of the security analyst is to identify whether the alert is a true positive or a false positive. Once they are done with that, and we know that the alert was a true positive, it goes for investigation and it goes to security analyst level 2. The level 2 analyst tries to assess the risks, the magnitude of the risks, and tries to find a way to respond. Also, they would want to determine the attack origin, the impact, and plan mitigations. In continuity, there's a level 3 analyst also. What they essentially do is they try to find the attacks that went undetected at the SIM level. So there may be some attacks that would be false negatives, and those would have to be hunted using some tech and some workflow in which we can identify if an attack happened or not. So we felt that we can use knowledge graph and generative AI in order to improve and in order to give more value to the defenders. For the context of this discussion, we started with CMDB. So CMDB is an essential part of security and network operations. While traditional CMDB gives us a good baseline for asset management, it falls short in connecting the dots across disparate data points. So if we were to understand the traditional CMDB, it would store data in tables or lists. And of course, when the data is being stored in tables or lists, the relationships are harder to keep track. Um there's a difficulty to adapt when a new asset type or a relation type is introduced in the traditional way of storing CMDB. And of course, it was not meant to visualize. So visualization is pretty hard there. There are certain things that we are doing using GraphDB, such as complex analytics, which is not possible in the traditional way of storing the CMDB. So what we have done is we have transformed the whole CMDB into a graph database to capture the true complexity of asset relationships. What that means is that the data will now be stored as nodes and edges, and the relationships across assets will be captured. Also, relationships across vulnerabilities and threats will also be captured by augmenting the CMDB data with other type of data, which I'm going to talk about in the subsequent part of the presentation. Also, it's very easier to add new asset types or relationships without modifying the base structure in a graphical database. And since it's a graphical database, it's naturally suited for visualization. In the later part of the presentation, you'll see that we are using algorithms like centrality, page rank, and a vulnerability priority score that we are calculating using the GraphDB algorithms, and we are trying to provide value to the defenders. And I'll just show you how. So moving on to tell you about the threat knowledge graph. So the source of inspiration from this was from John Lambert. So John Lambert was a distinguished engineer in Microsoft, and he mentioned that attackers think in graphs, whereas defenders think in lists. So by building this threat knowledge graph, what we are doing is we are providing that visibility of thinking in graphs for the defenders as well, so that it adds value and they can be at par with the attackers. So how we build this threat knowledge graph? So we built it in two stages. Stage one was we added the data from the CMDB as is, and we connected the relationships that were missing in the traditional CMDB. So this was stage one. Then in stage two, we added other data sources such as time interval logs, such as logs from VAPT or audit exercises. So VAPT is done when an organization wants to actively hunt for vulnerabilities that are present in the organization, and they want to identify the extent of those vulnerabilities. Using during the part of VAPT, a lot of tools like Nmap, Nessus, and Nikto are used. Even other tools are used so that they create logs which give defenders the visibility that what are the vulnerabilities that are there in the ecosystem, all that, what are the ports that are open. So in stage one, we have added data from CMDB, and in stage two, we have added data from the VAPT tools such as Nessus, Nmap, Nikto. And we plan to add data from audit logs also, but for the purpose of this demonstration, we have added just VAPT data, and we have put a GenAI querying system on top of it. And I'm going to do the demonstration now. So yeah. So as you can see, so just to refresh my screen, this is actually the way our threat knowledge graph is looking, and this threat knowledge graph acts as a single source of truth, because at different time intervals, data will be added to it. So it will also solve the problem of updating the knowledge graph, because whenever a BAPT or an audit exercise will happen within an enterprise, that data will get augmented within this knowledge graph, and it will keep on updating the knowledge graphs at different time intervals. So suppose I was a cybersecurity guy who was taking care of the enterprise data, and one point in time, a lot of VAPT logs and audit logs came to me, and I had to do patching. I had to identify if the vulnerabilities are true or not. I have to see what other resources will be affected because of the vulnerabilities that are present. Because one thing is getting the direct aspect of the device and the vulnerability. Another thing is if that vulnerability persists, what other devices can get affected by that. So for that, I have to sift through a lot of manual logs, go to CMDB, then go back to logs, do a lot of back and forth in order to identify all that intelligence. What we have done is we have tried doing it using generative AI by adding this threat knowledge graph as a source to it. So the first question that I'm going to ask is that what are the vulnerabilities that are listed as per the VAPT exercise that we did recently? So by asking this question, I'm trying to identify what were the findings of that VAPT exercise in short. So it very nicely gives us the answer that these are the 7 vulnerabilities that were found during the VAPT exercise. But now there's a very big question at my hand: which vulnerability to patch first? So rather than just doing my manual analysis, what we have done is we have used a lot of knowledge graph algorithms in order to come to a logical conclusion. So I'm asking this question to the LLM that what is the order of priority to patch the vulnerabilities found in the organizations, and it nicely gives us the response that RDP vulnerability is something that is essential. It has a priority score 9.8, and Sadashiv, my colleague, will go deeper into that, how we are getting this done. But this very nicely gives us action points that the first vulnerability that we need to patch is the RDP vulnerability, and the last one is the OpenSSH 7.6 outdated version. So this was one use case that we could solve using generative AI and knowledge graphs. The second use case is suppose, so just to give you a brief about the architecture, there are 3 Palo Alto firewalls. One is here, you can see second one here, and the third one here. So I want to identify that there's a Palo Alto firewall. What are the devices under Palo Alto firewall which are vulnerable? Just those devices and nothing else. So I'll do this query where I would want to understand return devices connected to Palo Alto which has vulnerabilities. So it gives 2 devices, PC1283 and PC1284. Now the defender, the security analyst knows that these 2 are the PCs under the Palo Alto firewall that we need to focus on. Also, they can see it in a side graph. So if you can see, this very nicely visualizes that this is the firewall, and these are the 2 red workstations that are vulnerable as per the latest VAPT exercise, and we need to patch. Now, the security professional has the visibility of thinking in graphs, and they can take actions accordingly. One thing I want to point out, again, building on what Dattaraj mentioned, is that once the data sources become multiple in nature, we will use agentic workflow to make this whole seamless. And Sadashiv, I'll pass the mic to Sadashiv, and he's going to talk more about the graph algorithms and the subsequent slides.
Hey, thanks, Venki. So am I audible?
Yes.
Yeah, thanks. So I'm Sadashiv Borkar. I am senior data scientist working with the CTO AI research. Knowledge graphs and Gen AI are the 2 areas which I focus on. So the application which we kind of developed, the threat KG, right? So this is the architecture design for it, right? So we have the CMDB, we have the time interval logs which are coming up for different intervals for various audits which are happening and so on. So we kind of extract them so that there are like different source data from which, like one is the logs, one is the CMDB, for which we will pull the data, store it into some kind of the storing staging data, let us say, and then there's a KG pipeline which will kind of pull this data into the KG, which is created in the Neo4j. Now this whole process can be an offline process. So but if you are doing it on a monthly basis, doing audit, let us say on monthly basis or on a quarterly basis, that's the time frame which you will kind of do this, pull in the data and update your knowledge graph with the recent with the recent logs and the recent data which is coming from the CMDB. Now then there is an online process where the SOC or the security assistant can kind of come and interact with this particular Neo4j, and that's where again the GenAI is the key. The GenAI layer is a key layer which kind of helps you to interact with the knowledge graph. So the various techniques we have used various techniques such as good amount of prompting with few short examples, and as well as tuning the models for text to cipher to other techniques which we have used to interact with the knowledge graph of various schemas. Okay, then there is a visualization layer which Venki showed us how the screen you saw things on the left hand side, how the screens were highlighted and so on. And then there is this LLM agent part. Now the LLM agent part here plays a key role in deciding which kind of algorithm you are going to fire at what, based on what kind of question which is asked by the user, right? So we're trying here with the agentic with the LLM agents as well, so that it takes a decision as to which algorithm it has to fire based on the query which is asked by the user. So this is like our architecture design which we have, and there are like these are the new project components which we have used. A quick next slide. Yeah. So these are the like algorithms which we have used, like the degree of centrality, page rank, and Dijkstra's source target shortest path. So degree of centrality, as we know, right, helps to kind of identify the popular nodes in the graph by measuring the connections and nodes. And this is where we use this algorithm to kind of identify the assets that are most connected with the network, right? This kind of helps us to determine which assets has the highest number of direct connections, and obviously that becomes like a critical asset in the network. Now page rank, right? The algorithm helps to determine how important is each node in your graph, right? How the connections coming in and from the other nodes and all, how those nodes interconnect, and how that particular device or that particular node in generic term is critical. Right? So we use this algorithm to kind of calculate the asset score. So there are multiple assets in your network, right? And you need to kind of identify how are you going to score that particular asset. So we use PageRank for it. So the score reflects kind of the asset's overall significance in the network. The Dijkstra algorithm, the shortest path algorithm, finds the shortest path between the nodes in the graph, right, using the positive weights of the connections and so on, right? So we are applying this algorithm to identify the most critical path within the network, right? So kind of this allows you to identify the routes which are in your network. Like let us say you are starting from a firewall to a workstation, and try to determine what is the most critical connection points and so on. So these are the three GDS algorithms which we have kind of used. So with that, I will quickly share my screen. I will show a few things what things are happening on the backend by sharing my screen. Let me know, please. Let me know when you guys can see my screen.
You can see it.
Can you see my screen? Yeah.
Yes.
Okay. Yeah. So this is like this is our data. This is where the complete data what we showcase. These are the nodes and the relationships what we have. This is like one of the queries which Venki used to identify what are the list of vulnerabilities which are there in the network. This tells you, this query tells you about what is there is a firewall called as Cisco, and what all assets are connected to that particular network and forms that particular LAN network. Then there is this query which this query returns there is a firewall called as a Palo Alto, and how many devices are connected to this firewall which has vulnerabilities being identified. So these are the same queries which gets kind of fired when you ask the question on the application. So that is just quickly show it. We also use the Bloom to kind of identify the different structure to kind of visualize how things look like. So very intuitive and explorative tool here. Then I have fired this question, right? Can you show me the critical path in my network starting from the firewall to workstation? So it gives you this descriptive answer, and this is where the GDS algorithms are fired off. So if you look at the graphical format of it, it shows in the graphical format that, hey, this is my firewall, and to this firewall there is a server, and then there is this VM to which the workstations are connected. So in my network, this I have selected this firewall. The reason for selecting this firewall, Cisco firewall, is because this has a higher centrality. So that's a logic, right? I have a higher centrality. The algorithm has been applied, which shows that hey, this firewall is high centrality, and from there I'm trying to find what is the most critical path by using the Jigsaw algorithm. Okay, so that's where I spoke about the agentic flow, right? When I fire such kind of query which requires the GDS algorithm to flow, then that's where the agents kind of take a decision to kind of run this particular algorithm to give you the critical path. While if I'm asking the question like, can you return the devices of Palo Alto which has vulnerables, then it kind of just shows what is there in the properties and all, and you can kind of nicely look at just what Venki showed, like what happens in the side graph to answer this particular question. I will just quickly finish off with this particular part. So this is like the Jigsaw algorithm which we used. So for this particular firewall, right, there are like various properties which kind of helps you to calculate like what is the asset score, what is centrality score, the vulnerability score, which Venki already spoke about. So we use those properties in this node to kind of answer those questions to find so that the graph can be enriched to kind of have the respective properties and the data to kind of get that question correct, and the relationships are getting populated with the score of the device score of the, let us say in this case the Cisco and this particular server. It kind of averages out to it. Device score kind of averages out to give the relationship score so that we can run the Jigsaw algorithm. So these are the few techniques which we use to kind of create this threat gauging. With that, I will just end my presentation if I open for any questions.
Thanks, Sadashiv. So just to summarize, we just have 5 minutes. You saw how we are leveraging for the modern cognitive architecture. We're leveraging knowledge graph data science, as well as large language models agents. And we see more modern systems having an amalgamation of this. These are the elements of the modern cognitive architecture. And you saw some examples of this. A few questions we saw in chat. So one is about the presentation. We'll make the PDF copy available, and we'll put some references also. There was one last question in interest of time. What are our thoughts on real-time countermeasures, decisions, and counterintelligence? So real quick, we saw the current network state as well as threat intelligence. And another part of it is something like an attack, MITRE attack, like a knowledge base. So and the attack knowledge base gives us some of these counterintelligence steps. So there are two aspects. One is historical data, how we have countered a particular attack. And second is if it is a new attack, we can figure out using some of the existing attack patterns, how you typically work around that particular attack, and we can capture that from data from that knowledge base, and using LLMs customize an answer. Again, an agentic workflow can pull data from multiple systems and give you a customized answer. So I think that is how you will typically handle countermeasure. Venki or Sadashiv, if you want to add anything to that.
You covered it very well, Dattaraj. I think that answers it.
So I think I covered it well. The agents would be the one which can handle the disparate sources going forward. That's a way to look forward by applying the agents.
Yeah.
Cool.
We can
so
connect
sorry.
We can connect the GenAI LLM based this thing to any data source, be it real time or be it maybe static sources also, and we can fetch insights. So basically the idea is to not have something rule based, rather we can have something based on NLP. So the analyst can ask as they think about any question. So the LLM will then make queries, and then the agents will help fetch relevant insights. Just wanted to add that.
Cool. Thanks, Venki. Okay, I think we are out of time. So thank you, everyone. Thanks for having us from Persistent. Join the session, and do let us know any other feedback, online or offline, and we'll work with the Neo4j team to make this presentation available. Thank you.
Thank you.
Thank you.